All right, so I'm doing an example right now of calculating the volume of a cylindrical shell. Here's the information that we have. We have the inner radius is B, we have the outer radius is A, and we have the height is H. So far, so good. I'm going to start by drawing a diagram. I'm going to do it over here, not like last time, so I have enough room for everything without erasing my diagram. I still like to draw my Cartesian coordinate system, even though we're going to work in cylindrical, because it helps me to organize my thoughts. So far, so good. Now, here's my situation. I have the inner radius, which is A. And I have the outer radius, which is B. And I'm trying to calculate the volume of the cylindrical shell with these dimensions and height H. Like that. So I'll draw it over here. That's the height H. How do I do that? First, I need to know the differential volume element. What is dV? We can do it by drawing a diagram. If I were to take a small chunk of this thing, let's say I take a little slice along Z, we're going to make it dZ like that. And I'm going to take a little angular chunk like that. And I'm going to take a little chunk depth-wise like that. That would be my differential volume element. That's what dV looks like. It's a little not quite cube of volume. What are the dimensions of this not quite cube so we can figure out its volume? Its height is dz. I already gave that one away. Its depth here is d rho because we're moving from some value of rho to a different, slightly larger value of rho. So that depth is d rho. Its width along this side is a little bit more complicated because it's not just d phi, because d phi doesn't have any length. Phi doesn't have dimensions of length because it's an angle. Instead, the length of that side, that's an arc length. If we're just looking down at the XY plane right now, and we have an angle here, and that angle is d phi, the length of this arc depends on the value of the radius, right? It's shorter here than it is out here, and it's really short close to the origin. So that arc length is rho d phi. That's true for arc lengths in general, except instead of d phi, you would put in the actual angle side. Because all of these, so that side length is rho d phi. I'll write that on there.
So then, quick question.
Yeah.
So then, d rho is actually just that would just be b minus a, correct? Or a minus b, because you
no, that's d rho is the differential length.
Oh.
Because the quantity that we are integrating is not constant along the variation of rho, right? Because the length of this arc length changes. So when we're integrating dV, right, we can't just stick with b minus a.
Okay, thank you.
No problem. Okay, so we've got that. And then here we are. The volume of our little volume element dV is the product of the three sides of the side lengths. You might think, this thing is not a cube. How can the volume of this thing be the product of the side lengths? Technically, it's not a cube, right? But because the side lengths are considered to be infinitesimally short because we're dealing with differential length, it is approximately a cube. And we do this in the limit that these lengths are so small that the volume of this tiny shape is the same as the volume of the cube. That's sort of the limit definition of an integral here. So that's how you do that. So the volume of this thing is going to be that arc length, rho d phi, times the depth of our tiny non-cube, d rho, times the height of our tiny non-cube, dz. That's our differential volume element. Now, how do we find the volume of this whole thing? We do an integral. It's going to be a triple integral of our differential volume element. How big is the differential volume element? It actually varies over the structure of our cylindrical shell. Let's talk about the bounds first. So the bounds are in z, we're going to vary from 0 to h. In phi, we're going to vary from 0 to 2 pi. And in rho, we're going to vary from a to b. Now I'm going to substitute in the expression that we found for dv, put it right here. So it's going to be rho. I'm going to put d rho next for reasons that you'll see pretty soon. And then d phi, and then dz. I can evaluate these integrals, the ones in phi and z, pretty straightforwardly because nothing inside the integral depends on phi or z. So I'm just having integral from 0 to h of dz, which is h minus 0, which is equal to h. Same thing in phi, I can integrate from 0 to 2 pi d phi, which is phi evaluated from 0 to 2 pi, which is equal to, oh, going off the screen there, 2 pi. Not too bad. So this triple integral that I've written out, shifted over a little bit, becomes 2 pi h times the integral of rho d rho from a to b. Don't let the fact that we're integrating a Greek letter throw you off. The integral of rho d rho is equal to rho squared over 2, just like it would be if you were integrating x dx. And then here we have to evaluate it over the bounds. So we were going from a to b. So likewise here we'll go from a to b, and we'll end up with b squared over 2 minus a squared over 2. So that's what we're going to sub in here. We also have to multiply it by that 2 pi h. So let me just do that this way a little bit. We've got 2 pi h integral from a to b of rho d rho, which is equal to 2 pi h rho squared over 2 from a to b, which is equal to 2 pi h b squared over 2 minus a squared over 2. Woo, I ran out of space. And like I said before, this is mathematically meaningful, but a little bit less physically meaningful. If you multiply it out, you can see that that is actually pi h b squared minus pi h a squared, which is the volume of a cylinder of radius b minus the volume of a cylinder of radius a. So it's like if we took the cylinder that's on the outside and then we just subtracted this inner cylinder to get just the shell.